Hello, students, and welcome to the Worksheet 7 video key. So we are going to be looking at chair conformations, which are conformations of cyclohexane derivatives. And cyclohexane derivatives can exist in two chair conformations, which we've labeled here A and B. And I really recommend that you make a chair, which is a 6-membered ring with all carbons, out of your models, right, your model kit, and play around with them to get them to be able to switch between different conformations of cyclohexane, such as the two chair conformations and even the intermediate boat conformation. So once you're in one chair conformation, what you can do is, for example, the carbon that's pointed down here can be flipped up. And in so doing, you should get into a boat conformation and then flip the opposite carbon down. And you'll be at the second chair conformation. Notice that we have a X, a red X, and a blue Y in these conformations. Both of these two substituents are pointed down, and we can tell that because the carbon here has what we would call an up hydrogen and a down X, and that's just based on which one is higher up on the paper or sort of above the ring versus below the ring. And then we have an up hydrogen on this carbon and a down Y. So both of these are considered down positions, and the hydrogens exist in the up positions, but they're not in the same position when it comes to axial or equatorial. What you'll notice is that the X here is in an axial position because it is either pointed straight down or straight up, in this case, straight down. And the Y is in an equatorial position. And after the ring flip, we have flipped from axial to equatorial and vice versa, but the groups are still in a down position. So if they start in a down position, they'll always be in a down position, regardless of which chair conformation they're in. However, they do flip between axial and equatorial in those two chair conformations. So again, this X went from down in axial to down in equatorial, and the Y went from down in equatorial to down in axial. Okay, moving on, we want to look at all of the different axial and equatorial positions all the way around the 6-membered ring. So notice here, again, this is carbon number 1, right? And we have a down in axial and up in equatorial. And then after the ring flip, we have a down in equatorial and up in axial. The axial and equatorial switch, right? Notice the blue going from equatorial to axial and the red going from axial to equatorial. But what was up, which is blue, is always up, and what was down is always down. Let's go ahead and add in the hydrogen atoms all the way around the ring. Or, I guess in this case, they just want us to label them axial or equatorial, not assuming that they're hydrogen atoms. Okay, so moving on to carbon number 2 here, right? You can see that one group is pointed straight up, so that'll be the axial position. One thing you'll notice is that axial will switch between straight down and straight up on adjacent carbons. So we'll go from carbon number 1, where axial was straight down, carbon number 2, where axial is straight up, carbon number 3, the axial will be straight down, carbon number 4, straight up, carbon number 5, straight down, and then carbon number 6, straight up. Right, so 3 of the axial positions will be straight up, and 3 will be straight down on opposite carbons. And then the equatorial positions are the ones that are not straight up or straight down. And the direction that you will see them in, they'll be parallel to a carbon-carbon bond in the ring, one bond away. So for example, this line will be parallel to this line or this line. right? And so we're going to label that equatorial and equatorial. Again, this line parallel to this line or this line. This line should be parallel to this line or that line. And so you'll see the equatorial position should all be drawn parallel to lines that are one bond away in the ring. Right? And you could do the same thing after the ring flip, right? So always pointed straight down or straight up, we have axial. Those will alternate. And then the equatorial. Okay. I think I did everything that it said in carbon number 2. Or, sorry. Question number 2. Okay, so next it talks about, without having the lines drawn in for you, let's learn how to draw the axial and equatorial lines, right? And so it shows you an example, right, of axial and equatorial. And you can also look at what we had just done in the previous question. What we want to do is we can go ahead and draw in all the axial. And again, we're just going to either point straight up or straight down, and we're going to alternate. Right? So straight up, straight down, straight up, straight down, straight up, and straight down. And that will be all 6 for us. And then for equatorial, remember we want to do, we want to look for the parallel lines. So the equatorial position here should be parallel to these 2 lines because they're one bond away in both directions. So looking at and trying to draw a line parallel to this one, I can draw it in like here. And then this one, equatorial should be parallel to those 2 lines. Right, these are the trickiest ones actually, these 2 in here. But again, if we look and see what lines they should be parallel to, we'll know exactly what angle. Students like to draw them sort of in random angles like in here. What we can see is that this line should be parallel to the equatorial line. So I need to draw it there. And then here, parallel to those 2 lines. So that one's already drawn in for us. And then this one here, because it should be parallel to that line and that line. Okay, and then we can do the same thing over here, right? We can do all the axial positions. So again, we're going to just do from these 2 that are sort of higher up, right? Those are going to be straight up. And then this one that's lower down will be straight down. Sort of straight up, right? At those 2, this one will be straight down. We just alternate. Okay, and we can label all those axioms. And then the equatorial ones, those are a little bit more tricky, but we just have to look and see what line they should be parallel to, and we should be able to put those in. Okay. So hopefully you can start to see how to draw in those axial and equatorial positions, right? And so I think the question here wants us to locate exactly where these substituents are in this chair and then figure out where they will be once we do a ring flip, right? So remember that what's up always stays up, right? So the fluorine is up. What's down always stays down, but it does flip from axial to equatorial. So since this fluorine is axial, it should be equatorial after the ring flip The bromine is currently equatorial, so it should be axial after the ring flip. So one of the things that I like to do to sort of orient myself is to finding this particular carbon in this structure over here is to look for the carbon that's either pointed down or pointed up at the corner, right? Because the one that's pointed down at the corner, think of it as like this one that I've sort of put a little green dot on, will end up flipping up and will become that carbon after the ring flip. So if this carbon is this carbon, then we sort of go clockwise one, that will end up being such that the blue carbon here that we're looking for, right, is now here. So this is the carbon that's going to have both the fluorine and the bromine. And we can draw in the axial and equatorial positions on those. So this one, the axial would be straight up, so this is going to be straight down, right? And then the equatorial position will be parallel to this line and this line, right? Since it's one away. We want to kind of draw it up to the left here, right? And so we talked about the fact that what is axial will become equatorial, but it will still stay up, right? Because the fluorine is up, so fluorine will be up over here, but it went from axial to equatorial. The bromine will stay down, but it goes from equatorial to axial. Okay, so let's keep working on these. So let's do this next one here. Right, so these two carbons are the ones that sort of flip up and down. So they end up pointed the opposite direction in the other one. So this one is, I think, fairly easy because it ends up still at the two easier to identify carbons. Right? So this one right now, bromine, notice how it's up because the hydrogen here would be down. It is up and equatorial. So after the ring flip, it should be up and axial. Put it in the up position here. And then the fluorine right now is up and axial, so it will be up and equatorial after the ring flip. Okay, moving to this one over here. Again, notice that this carbon that's flipped up will end up flipped down. Right? So the two carbons that we'll be placing groups on are the ones attached to that carbon. And just notice that sort of going clockwise, right, from this carbon that was flipped up, becoming flipped down, we have the OH group. Right now it's down and axial. So after the ring flip, it should be down and equatorial. The equatorial position here is pointed this direction, should be parallel to this line or this line. It will have the OH group. Right, and so the fluorine right now is down and axial as well. So again, it should be down and equatorial after the ring flip. And the equatorial carbon is pointed in this direction here. So either this, sort of try to get it parallel to this one or this one. And the atom there. Okay, and then now we have a cyclohexane with 3 substituents. Notice that this carbon is flipped up, so it will be the one that ends up flipped down. The methyl here is up and axial, so it will be up and equatorial after the ring flip, which will be here. Right, and then if I'm going sort of clockwise, I come after 2 carbons, I get to a carbon with a bromine that's equatorial and down. Okay, so 2 carbons going clockwise would be this one. And I need my bromine, again, now down and axial. And then 2 more carbons sort of going clockwise, and we'll end up at the other carbon with a methyl. Right now it is axial and up, so it should be equatorial and up after the flip, which would be here. Okay. So the next question says, make a model of tert-butyl cyclohexane And so you can use your model kit to make a model. Draw the two chair conformations of tert-butyl cyclohexane and explain why you think one conformation is lower energy than the other. Okay, so we can go ahead and draw two different chair conformations of cyclohexane. And again, if you have trouble seeing this, I encourage you to use your model kit. So when I start from scratch in drawing a chair conformation, I like to draw my two parallel lines. And I can start with one chair, which will go down and to the right. And then slightly lower than that, we'll do a parallel line, something like this, right? And then from here, I can go 90 degrees from the first line and then connect the two. This is one chair conformation. And it says it should be tert-butyl cyclohexane, and you can put it anywhere, right? So for example, perhaps I will put it equatorial here. I'm going to put it equatorial, and I'm going to make sure to draw it like, drawn out, just so that I can kind of see the size of it. Right? So a tert-butyl is like a carbon, and each carbon has a methyl group attached to it. So it's a really bulky group, as you can see. If you just wrote TBU, that's okay. That can abbreviate tert-butyl. But this one really kind of shows you how large it is. And it didn't ask us to draw in all the other hydrogens. And if you had wanted to, you certainly could do that. And just for fun, we'll do that as well. Right? So we have the hydrogen that's up and axial. And we have our hydrogens all around. I'm just going to do this quickly. Hopefully you're getting pretty good at this point. Lots of practice in and hopefully with the lecture video. Okay, so those are all the other hydrogens. Now let's go ahead and do a ring flip. Right? And so to do the other one, so for this one, I sort of started and went down and to the right. So the other one, I can sort of start from the top and go down and to the left, or start from the left and go up and to the right. So either way that you want to do it should work fine. Right? So maybe something like this to start with, and the other parallel line, as parallel as you can get it. And pairs never end up perfect, but hopefully they're fairly close, right? You can always extend a line a little further if you think you didn't quite get it perfect, right? And then connect. Okay. And now we want to see, okay, where was my tert-butyl? Well, I ended up putting it at this carbon. You could have put it anywhere, but I chose to put it here in equatorial. So it was down, and it's going to remain down, but it's going to go into an axial position. We'll go straight down here, right? And then I'm going to draw in all my 3 methyls. And then we can go ahead and add in all the other hydrogens. Noticing the angles, make sure you get the angles of those equatorial hydrogens correct. Okay. And then it says to explain why you think one conformation is lower energy than the other, right? And so what we'll see here with this tert-butyl group when it's in an axial position is that it ends up that the hydrogen here that are axial at the other carbons that are also pointed straight down, right? These are experiencing steric strain, right, with the entire bulky tert-butyl group. Right? Whereas the hydrogens are much further away from those axial hydrogens, or any other hydrogens actually in a equatorial position. And again, it can be really easy, much easier to see this in a model, a 3D model, than on 2D paper. Right, so definitely the favored conformation is the one where the tert-butyl is in an equatorial position. Just go ahead and add that in. Okay, so we call this 1,3 diaxial strain. The reason why it's called that is if you called this carbon number 1, right, then if you counted 1, 2, 3, this would be carbon 3, and the 2 axial groups. So it's the relative position of 1, 3 in either direction, right, with the groups in the axial position. Those are sterically crowded and they form what we call 1,3 diaxial strain. Okay. So this one is more stable, right? Stable at equilibrium. Okay, so and this just gives you a little bit more of a hint here about what's going on with the close groups, right, in the axial positions. Okay, moving on. We've been talking about groups that are up and down. So hopefully this is not a section that surprises you, right? Where we talk about that groups are either up or down on a chair conformation. And the one that's up is always sort of further up, right? And the one that's down is always further down at any given carbon. And those actually refer to positions in a dash wedge notation of the same cyclohexane group. And you can see that groups that are up are always on a wedge. Groups that are down are always on a dash, right? So if we have to go between the two, we know that if we have a group on a wedge, we should make sure to put it in an up position as opposed to a down position, because you actually won't draw the correct structure if you end up putting a group that is on a wedge in one of the down positions. Because remember that up is always up, right? So regardless of the chair conformation, if it's in an up position, it's always in an up position. You can't just flip those two groups. And the reason for that has to do with something called stereochemistry, which we'll talk more about in chapter 5. Okay, so let's go ahead and practice. And it says, draw the 2 chair conformations of each of the following molecules and circle the more stable chair conformation. So let's go ahead and do that. So remember how we talked about drawing those chair conformations? Start with 2 parallel lines that are slightly offset. And the one that's drawn further up on the page should be sort of extended further up. And then we have, right, the 90-degree angle lines and connect them. You should have a pretty nice looking chair conformation. And then we can do the opposite, right, to draw the other chair conformation. So instead of down and to the right, we do up and to the right. So again, slightly offset the lines. Okay, those are our 2 chair conformations. And then let's put in these 2 methyl groups, right? So recall that this methyl is on a wedge. It should be in an up position, right? So it doesn't matter where I place it on here, as long as it's in an up position. You cannot place it on a down position. That would be considered wrong. Right? So let's say I place it at this carbon, right? Then I want to place it in an up position. And the up position at this carbon happens to be axial. Right? So I'm going to do, again, this is the up methyl, and it's placed in an up position. At this carbon, the up position happens to be axial. And then if I'm going clockwise, I run into another methyl that's down, right? So this needs to be in a down position. At the carbon that's one clockwise from it, the down position is also axial. Right, so we have happens to be up in axial and down in axial. And then when we ring flip, this carbon that's pointed up will flip down, right? So it ends up being this carbon. And the methyl group there needs to remain up, but it does change from axial to equatorial. So we'll change, right, this methyl group to from axial and up to equatorial and up. And then this carbon then becomes this one. And again, it has its methyl that's currently down in axial and needs to become down in equatorial. And that position should be, that line should be parallel to this one. Go ahead and draw that in and add the methyl. Now, which one of these is more stable? It says circle it. We can also indicate that with an equilibrium line, right? So we could do something like this. This tells us that this one is more stable because the equilibrium will favor it. The reason we are doing that are because the methyls are equatorial over here versus axial. And again, axial will have 1,3 diaxial strain. So we'll just circle this one because it told us to circle it. Okay, moving on to the next one. Again, we can start by drawing our two sort of generic chair conformations. Hopefully, as you practice this more, you get better at it. Never end up quite perfect, but you do a pretty good job here if you practice. Okay, those look pretty good. So now we just need to put in our methyl groups. Again, both of these are down, right? So you just kind of choose where you want to start. I'm just going to start at a different carbon just to show you that I can, right? So sometimes students get really like, okay, if I started here, right, would it have been okay to do that as opposed to starting here? So like it doesn't, we don't know exactly where these carbons are. They could be anywhere, right? So we can, I'm just going to choose, like last time I took this carbon and started it here, right? But just to show you that you can start anywhere, I'm going to start at a different carbon. So for example, perhaps I might want to start at this carbon, right? Let's go ahead and start there. So now I have a down methyl. So at this carbon, the down position would be axial, right? And then if I go two clockwise, sort of moving two clockwise, I need another methyl that's down. And again, the methyl, and it's not easy to draw because it kind of ran into one another, but the idea is that they're both down and axial in this case, right? And then after the ring flip, this carbon is going to flip down. So my carbons that have the methyls are going to be here and here on either side. And again, they're going to be down, but they're both going to flip to equatorial. So we'll have the methyl here and then the methyl here. Right, so definitely more stable when they're both equatorial and both axial. All right, moving on to the last one. Now we have, again, we're going to start with a sort of a generic chair structure. And sometimes I kind of joke that Art 101 needs to be a co-requisite or a prerequisite of this course, just because there's so much drawing involved, freehand drawing. Okay, so again, we can kind of start anywhere, right? As long as we make sure to put these groups either up or down as indicated in the structure, right? So I can start anywhere. So let's say maybe I want to put this terbutyl group at this carbon and put it in a down position, which would happen to be equatorial, right? So I'm just going to put my TBU. right, which stands for tert-butyl, which is this group, right? And it is in a down position, so that's good. And then if I sort of go clockwise, right onto the 3 carbons away is a down methyl, right? So we'll go down over here. Methyl. So this carbon, right, ends up being this carbon, and then the tert-butyl still needs to remain down. So it ends up coming down and axial because it was down in equatorial before. And then, right, 3 carbons away, we end up with this one that is, there's a down methyl, and it was down in axial, and now it's going to be down in equatorial. And it's, again, if you chose to start at a different spot, that's okay. The only thing I like to remind people is sort of wherever you do start, right? If you're working clockwise here to get to the next substituent, work clockwise here to get to the next substituent, as opposed to going counterclockwise, because then you could end up accidentally drawing the wrong structure, which will make more sense after chapter 5. Okay, so between these two, what's more stable? Well, in this case, we have a methyl group that's axial, but the much more bulky tert-butyl group is equatorial. So that's definitely going to be more stable than getting the bulky tert-butyl group axial just to get the methyl group equatorial. So in that case, we'll want to draw our equilibrium favoring that more stable structure. And then the last part of the activity talks about converting something that's in a chair conformation back to a structure with dashes and wedges. So we can just look at the fact that, right, up needs to be on a wedge and down needs to be on a dash, and then make sure to follow that when we come over here to the regular dash wedge notation. This one just has 4 methyl groups at opposite carbons, and one is up and one is down, right? So we can just kind of go, one is up, one is down, and then draw the same thing at the opposite carbon. Okay, so moving down here, right, we just want to draw this hydroxyl group is in an up position, so it needs to be in an up position. And again, you can start anywhere, right? Doesn't matter as long as I'm clockwise from wherever I started. So for example, perhaps I could place this up hydroxyl right here. Right? Then I just need to work clockwise, right? So now I also have an up methyl and another up methyl on adjacent carbons. So we'll make sure to place those in. And then I have just a CH2 and another up methyl. Okay, moving right along, we've got a carbon with an up methyl. And again, you can start anywhere. I'm going to choose to start here. I'm going to work my way clockwise. So skip a carbon, go to one that has a down methyl. You just want to place that on a dash. Okay, moving over here. Again, I can start anywhere that I want to. Right, let's start with this fluorine that's down. Right, maybe I'll place it right here. That fluorine is down. Then I just kind of like to work in a clockwise direction. So skip one carbon, and I have a hydroxyl group that's also down. Right, and then I skip 2 carbons, and I come to a fluorine that is also down. Okay, moving on to this one. Let's start with the bromine, right? I can start anywhere I want, so I'll start with the bromine. I notice that this bromine is down. So I'm going to put this bromine here. And then I'm going to go clockwise, and I'm just going to skip 1 carbon, do a methyl that's up. And then I can skip 1 carbon and do another methyl that's up. And then here I have 2 chlorines. I can start anywhere. This one is up. So I'll start here. And then I skip one carbon, come down to another carbon that has a chlorine that is down. Okay, so that is the end of this activity. Let me know, as always, if you have any questions.